Mm-hmm.
For the test on Thursday, it is gonna be what we covered in 5 to 6.
And 7. Yep. So I'm going to pull effectively one of these problems, probably the first one, because I think it was significantly easier than the second one. Second one, you had to do a little bit of thinking about how flux splits up and all that kind of jazz. So something similar to problem 1 off of this, and then I haven't decided what I'm going to do. But like one problem from homework set number 6, one problem from homework set number 7, 10 points for literally writing your name down correctly, as per usual. All right, so this is the problem. This is the first problem that you guys were given. So we have an electromagnet that's used to lift sheets of steel. The coil has some number of turns and a resistance of 5 ohms. The magnetic core has a square cross-sectional area of 25 centimeters squared, which means it's a 5 centimeter by 5 centimeter cross-section. Its reluctance is negligible compared to that of the air gaps, meaning effectively that we only care about the reluctance of the air gaps. When a sheet of steel is lifted by the electromagnet, air gaps of length 1 millimeter separate the electromagnet and the sheet of steel as shown below. If the average force required to lift a sheet of steel is 500 newtons, determine the DC source voltage required to lift the sheet and the energy stored in the magnetic field during the lift. And part B, I was actually impressed that you guys actually noticed something that I didn't, that made it way easier to do. But anyway, so. All right, so let's work on part A here. We're trying to find the DC voltage. And so in order for, in order for us to find the DC voltage, we are going to have to find the current that's flowing through our coil. So this is literally going back to our Ohm's law for magnetic circuits style relationships and all of that kind of stuff, right? So let me just put down here what our parameters are. So this is homework number 5.1, right? So we know that our coil N has, I think it was 400 turns. Our resistance R was 5 ohms. The core area was 5 centimeters squared, and our gap length was 1 millimeter. And our mechanical force was 500 newtons for what it's worth. All right, so we're trying to find the DC voltage required to lift a sheet of steel under the constraint that the air gap is going to be 1 millimeter. So this is just going to be some DC current that we need to solve for times the resistance of our coil, which is given to us to be 5 ohms. So solving for IDC is the majority of the work in this problem, okay? Now we know that MMF, which is just N times I, and I'm going to label this as IDC, is equal to magnetic flux times reluctance, right? And so rearranging this, we can say that our current flowing through our coil has, which I'm going to call phi G, because we're only going to deal with air gap quantities since we are told the reluctance of the core doesn't remotely matter, times our equivalent reluctance, which is also only going to depend on the air gaps, divided by our number of turns. Okay. So let's figure out our equivalent reluctance. We have two identical air gaps. So I'm going to have 2 times the length of my air gap divided by the permeability of my air gap, which is mu naught, times the area of my air gap, which is going to be 5 centimeters plus LG squared. Okay. So putting numbers into this, that's going to look like 0.2 centimeters divided by 4 pi times 10 to the minus 9 henries per centimeter times 5.01 centimeters squared. If I throw this into my calculator, I get 0.2. Let me clear all this crap out. Multiply that by 2. You're right, 5.1 centimeters. Thank you for that. And let me fix that. So 0.2 over 4 pi times 10 to the minus 9 times 5.1 squared, 6.119 times 10 to the 5 amp turns per Weber. Alrighty, so we figured out our equivalent reluctance. Now we need to figure out how to determine our magnetic flux, right? So, and I'm doing this from memory, so I'm going to pre-apologize if I made a mistake on this equation here because I did not bring the notes for that material. But I believe that our mechanical force was equal to the flux in our air gap squared divided by twice mu naught times the area of our air gap. And then there would also be a term for the core, but since we know the core is negligible here, it's not going to contribute anything. So can anybody, before I use this, verify that this expression is correct? Okay. So I could rearrange this thing and say that BG, the magnetic flux density in my air gap, is going to be equal to the square root of twice mu naught FM divided by AG, like so. Anybody have any beef with the algebra I've done there? Hopefully fairly straightforward, just rearranging stuff and solving for BG. Okay. So let's go through things here. So 2 is just a constant. Mu naught is 4 pi. And I'm going to choose to express this as 10 to the minus 7 henries per meter, where a henry is a volt second per ampere. And then our force is 500 newtons. Well, a newton is a joule per meter, and a joule is a volt amp times a second. So I'm going to have volts, amps, seconds per meter. And then that's all going to get divided by the area of my air gap, which is 5.1 centimeters squared. And then I'm going to multiply that by 1 meter is 100 centimeters and square that conversion factor. And then all of this is to the 1/2 power because that's the same thing as doing the square root. So I've made the units this mess of things so that we can see exactly what's happening here, right? So the amp here cancels the amp here. This centimeter squared is going to wind up canceling this centimeter squared. And so what I'm going to be left with is volt seconds squared, which looks like Weber's squared. And then I'm also going to have meters to the 4th power. So I have volt seconds squared divided by meters to the 4th power, which is the same thing as a Tesla squared. And then when I take the square root of that whole thing, I'm just going to get a field measured in Tesla. So that's why I've chosen to express the units like this so that we can make sure that what's coming out of this expression is going to be in Tesla, where a Tesla is by definition a volt second per meter squared. Okay. So putting this in my calculator, I have 2 times 4 pi 10 to the minus 7, 500, 5.1 squared times 1 over 100 squared, 0.483. Now I take the square root of that answer, and I got 0.695 and some change Tesla as the flux, the flux density in my air gap. From here, my magnetic flux in my gap is just going to be my magnetic flux density times the area of my gap, right? So 0.695 Tesla times 5.1 centimeters quantity squared. And then times 1 meter per 100 centimeters quantity squared. So this is going to give me some number in Webers. Okay. So multiply that by 5.1 squared. Multiply that by 1 over 100 squared. And I get 1.808 times 10 to the minus 3 Webers. And now my DC current is my flux. So 1.808 times 10 to the minus 3 Webers times my equivalent reluctance, 6 times 10 to the 5, if I'm not mistaken. Amp turns per Weber divided by my number of turns, which is 400. And we should see here that Webers cancels per Webers, turns cancels turns, and we're just going to get an answer in amps. So let's see, multiplies. Scroll back up here so I don't have any rounding error to deal with. Where that is X, that is Y, X times Y divided by 400 comes out to be 2.766 and some change amps. And therefore our DC voltage is 2.766 amps times 5 ohms comes out to be 13.828 volts. Which I think is the answer on the sheet. I'll be damned, I got it right. Crazy how that works. All right, so to calculate our stored energy, the way that I did it was I said that WF was BG squared over twice mu naught times the volume of our air gap, which is just our air gap times the length, our air gap area times the air gap length. Some of you were paying way more attention than me, which is wonderful, and realize that this is literally just the same thing as the mechanical force times the air gap length. And so you actually didn't need to do a lot of the math that I did. You could literally just multiply two numbers together and get the exact same result. So kudos to you guys for actually thinking about things. I can't believe I didn't notice that. Frustrates me slightly. That's okay. So 500 newtons times 0.001. Actually, it should be 2 millimeters because there's two gaps. So 500 times 0.002.
Because it travels only 150.
Okay, sure. 0.5. This realistically is actually the energy stored per air gap. Yeah. So my answer on the sheet, I want the energy stored in the magnetic field during the lift. So realistically, it should actually be 1 joule because there's two air gaps that are storing energy. So I'll need to fix that, but process is fine. I just didn't think about the fact that there were two of them for whatever reason. All right. So that was problem 1. Problem 2 is something pretty similar, except that we have an odd shape. So we're gonna have to pay attention to what's going on with this guy, right? So effectively, we have a coil on that central leg that's going to be driving some amount of flux around this magnetic circuit. So let me go to draw here and let me figure out how to change the color. So I've got some flux here that I'm going to call phi mid. And then that flux is going to split off like so, and like so to complete the magnetic circuit. And so I'll call this phi left and right. And because our circuit is it sees those two identical paths effectively in parallel, we know that this is just going to be 1/2 of whatever flux we have flowing through the middle leg. So I'm going to wind up using that to figure out the magnetic flux density in each of those air gaps, and I'm going to use those to do my energy storage calculation. Okay. All right, so let's look at this thing here. We're told, so this is homework number 5.2. our number of turns is 2,500. The magnetic flux density is 1.25 Tesla in the middle air gap. So let's say that B mid is 1.25 Tesla. It literally says below the coil. Yeah. Yeah, that's okay. No, but I specified it because I did not want any ambiguity because there are 3 different air gaps and there are 2 different air gap sizes. And so specifying which air gap is carrying that particular flux density is very critical to actually being able to work this thing out. So. All right. The air gap length is 2 millimeters. And we also have some dimensions here, right? So my middle gap is going to have an area of 40 millimeters plus LG squared, because we're told that it's 40 meters or 40 millimeters wide and then 40 millimeters deep into the page. And then our left and right air gaps are going to be 20 millimeters. I wrote 200 instead of 20. Times 40 millimeters plus LG, like so. So I'm going to go ahead and write those down, right? I'm going to express these areas in let's do square meters. So 0.042 squared is going to look like 1.764 times 10 to the minus 3 meters squared. And then the area of the left and right air gaps is 20 millimeters plus LG times 40 millimeters plus LG. So that's going to look like 0.022 times 0.042 or 9.24 times 10 to the minus 4 meters squared. All right, so we're trying to find our current. And so effectively, it's going to be extremely similar to what we did in the last problem, right? So without doing any lengthy derivation or anything, we know that our coil current I is going to be the flux through the middle leg times the equivalent resistance seen by the coil divided by the number of turns in the coil. Our equivalent resistance is going to be, or excuse me, the equivalent reluctance is going to be the reluctance of the middle air gap. So that's going to be LG over mu naught A mid. And then I have the reluctance of one of the legs, the left or the right air gap. So that's going to be LG divided by mu naught A left right. But because those two are in parallel, that's going to cut that reluctance contribution in half. Everybody okay with that? So if we look at our flux path, we see that the flux flows up through the middle and splits and circulates back around. So effectively, if I were drawing this as a circuit, I would have my MMF source with the reluctance of the mid, and then I have the reluctance of the left and the reluctance of the right, like so. Or I just chose to move the branch with the MMF over to the left-hand side to make it easier to see what's going on. Right, so it's only the left and the right that are really in parallel because we've got this foil generating our MMF through that leg. Okay. So I've got all the appropriate numbers written up here, so I'm just going to put this in my calculator. Let's see. So LG is 0.2 centimeters divided by 4 pi times 10 to the minus 9. So that'll be henries per centimeter. And then I have my middle, so that's 1.764 times 10 to the minus 3. And that's in meters squared. And there are 100 centimeters per meter, so I'm going to have to multiply by 100 squared. And so that looks to me like 9.022 times 10 to the 5. Now I'm going to do the second term. So we have 0.2 centimeters divided by 2 times 4 pi times 10 to the minus 9 times 9.24 times 10 to the minus 4 times 100 squared. That looks like 8.612 times 10 to the positive 5. Both of these are in amp turns per Weber. Adding them together, I get 1.763 times 10 to the 6 amp turns per Weber. Pi mid is going to be B mid times A mid. So that is, let's see, 1.25 Tesla, so Webers per meter squared, times 1.764 times 10 to the minus 3 gives me 2.205 times 10 to the minus 3 Webers. And so plugging in our numbers, I'm just using the equation that I wrote up here. So that's going to be Z times T divided by 2,500. 1.555 amps. Let's just check here. Oh, I got a vastly different number. All right, so let's just take a look at this and make sure there aren't any mistakes. That probably would help if I had written down numbers, but I didn't. Let me just go back through my calculations here. So 0.2 centimeters, 4 pi times 10 to the minus 9, 1.764 times 10 to the minus 3, and that's per centimeter being multiplied by meters squared. I'm not seeing any errors. The process is correct for what it's worth. Yes.
Then how you got the area for left, right?
Okay. So let's look at that really quickly. So we're told right here that the width of the left part and the right part, 20 millimeters wide. And it's also 40 millimeters deep. Because we have an air gap, we increase the dimension by the air gap length in both directions. So it should be 22 millimeters by 42 millimeters. Yeah. I'm going to throw a circle around that for now. I think that's correct. I'll have to figure out whether I made the mistake here or whether I made the mistake in my solutions that I was knocking out 5 minutes before class. But anything about this process seem incorrect. Let's start there. Numbers are arbitrary. That's just a calculation error. Anything about determining my equivalent resistance or reluctance seem suspicious. It's just the reluctance of the middle air gap plus half the reluctance of the left or the right air gap, because those two air gaps appear as if they were in parallel to our MMF source. Okay. So this equation seems appropriate. The equation for our flux is just magnetic flux density times area. So pretty hard to screw that one up. Multiply those two things, divide by N, because that's just rearranging our Ohm's law for magnetic circuits relationship in order to find current. That's pretty straightforward. We've been doing that for a while. So feel, unless I just type something into my calculator wrong, that this is the correct answer. So let's just go from there. All right, so now that we have our current, we need to find our stored energy, right? And so our stored energy is going to be, let me do it this way. So this is the stored energy from the middle air gap. So that's going to be B mid over 2 mu naught times the area of the middle air gap. And then we're going to have B left and right divided by twice mu naught times the area of the left and right air gap. So that's the contribution of one of them. But because there are two of them, I need to put a factor of 2 out here. And actually these magnetic fields are supposed to be squared. So we know B mid, we know mu naught, we know our areas. We don't know B left and right. So how are we going to figure that out? Yep. So B left and right is going to be the flux for the left and right path divided by the area for the left and right, which is just going to be 1/2 the flux in the middle divided by the area of the left and right. So coming back down to here, we're going to have B mid squared over 2 mu naught times A mid plus this 2 and this 2 cancel. So we're going to have phi mid over 2 area left and right, this whole thing squared, times the area of the left and right, which looks like B mid squared over 2 mu naught, A mid plus phi mid squared over twice A left and right. I'm sorry, what? You are right, it should be 4. So phi mid squared's 4 A left and right, 1 A left to right on top. So we're left with 1/4. Yeah, okay. And so from here, we can just plug in our numbers. So I forgot it. U naught. There we go. Let me put this over here. A left to right divided by mu naught. Yes, okay. Thank you for that. 1.25 squared divided by 2 times 4 pi times 10 to the minus 7. And then our A mid is 1.764 times 10 to the minus 3. And for this guy down here, we have phi mid squared, which was 2.205 times 10 to the minus 3 squared divided by 4 times our area, 9.24 times 10 to the minus 4. Doing everything in terms of meters here, so this mu naught should be 4 pi times 10 to the minus 7. add that. And then A plus B. We got 2.143 kilojoules. Oh, kilonewtons, because we're dealing with force. Okay. So I must have made some dumb mistake calculating the current because I got. Oh, okay, I see what I just did. Sorry about that. Ba, 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 ba. I called this WF, but this would actually be FM because I was multiplying by the area and not the volume, right? So for the field energy stored, I multiply by the volume, not the area. So I can just take this number right here and then multiply it by LG to get my mechanical force. No, multiply it by LG to get my stored energy, sorry. So WF will be FM LG, so times 0.002, 4.287 joules. I'll have to go through my MathCAD sheet and see where I screwed up calculating that current later. Yes. So I might have just forgotten to say that they were in parallel or something like that. Mm-hmm. It gave you the answer that I had written down, which, so the reason why it shouldn't be just one of the left or the right, the reason why it should be 1/2 is because we have those reluctances, but they are in parallel, right? Yeah, so the answer on the homework seems like it is incorrect, but it also seems like you just figured out where my mistake was because you accidentally made the same thing. Or we probably didn't make the same mistake. Actually, you were trying to get the answer that I had written down as more likely. Correct. Yeah. So I'm positive that Skylar was, you're talking about the grader, right? She was just looking at my MathCAD sheet and she saw that I made that mistake and so she said, well, presumed I was correct, which it looks like I was not. So I'll have to make her go back through and regrade homework problem 2 here. But let's recap that calculation of REQ just to make sure we're all on the same page, right? The reason why this factor of 1/2 is here at all is because those two paths are in parallel. So if we throw away this factor of 1/2, this contribution right here, LG over mu naught times the area of the left or the right gap, is just the reluctance of one of those gaps. We have to take into account the fact that there are two gaps, one on the left and one on the right. And the correct way to do that is to notice that they are in parallel, which means we should have half the reluctance. We can't just throw one of them away. It's either going to be a 2 on the denominator here because they're in parallel, or a 2 in the numerator because they are in series, and they're very much not in series by inspection. Yeah. But now we know where the error was. So that's a pretty easy fix. I literally just go back in my MathCAD sheet, type 0.5 in front of that term, and we'll get the numbers that we got here. So, okay. So homework set number 5, done. I have that 12-part long example problem that we didn't have enough time to do at the end of our last class meeting. That really kind of encapsulates everything I expect you guys to be able to know about the induction motor side of things. So do you want to do that problem or do you want to look at homework problems? I don't know that we have time for both. Okay. So let's look at homework set number 6. So this is literally just, problem 1 is literally just applying a single equation. So I'm not going to bother with this one too terribly much. Just as a heads up, let me find the correct equation. So NS is equal to 120 times frequency divided by the number of poles. So you're literally just doing 120 times 60 hertz divided by 2 will give you 3,600 here and so on and so forth. There's enough information to just apply that equation a whole bunch of times and figure out what the speeds will be for different motors here in the US, here in Europe, based on the number of poles and their operating frequency. So that's easy enough, yes.
I didn't write out every single one, but I just wrote them these that use like that equation.
Mhm.
Am I gonna get dog and homework because I didn't show my work?
I'll talk to the grader and make sure that you don't get penalized for that, because I mean, it is literally the exact same equation over and over and over again. So writing it down 15 times seems pointless to me. So I'll make sure that I express that concern. Yep, nope, that very reasonable. All right, let me see what's going on in the chat here. What is the date of exam 2? It is Thursday, which would be February the 1st, maybe? Yeah. All right, so problem 2, we have a 3-phase 60 hertz Y-connected induction motor that has a shaft speed of almost 120 RPM at no load and 114 RPM at full load. We want to know the number of poles of the motor, the slip of the motor, the angular velocity of the motor, and the slip frequency of the motor. So for part A, it's literally just applying that equation from earlier, right? So if we rearrange that equation, we would find that the number of poles is equal to 120 times our frequency divided by our effectively unloaded shaft speed. So that would be 120 times 60 divided by 120 equals 60 poles. Easy enough. For part B, we want the slip, right? So slip is defined as NS minus NM over NS. So that should be 120 minus 114 over 120 is 1/20th or 0.05, which is the same thing as 5%. Easy enough. Omega M, the angular velocity of the rotor. So omega M, so that is radians per second. That is going to be related to NM. So that's revolutions per minute, right? So let's look at the units here. Rev per minute. And I need to get this into radians per second, right? So I'm definitely going to have to multiply this through by a factor of 1 minute is equal to 60 seconds, right? So that's going to give me revolutions per second. And then there are 2 pi radians per revolution. And so my revolutions cancel, my minutes cancel, and I wind up with radians per second. So 114 times 2 pi over 60, 19 pi over 5, or 11.938 radians per second. So it looks like the conversion factor to go from speed in RPMs to angular frequency is just multiply by 2 pi over 60. For part D, we're trying to find the slip frequency of the motor. So that slip frequency FR is just S times FS. So that is 0.05. Let's see, did I give you? Oh, times 60 hertz. So 1/5 of 60 hertz should be 3 hertz. So problem 2, pretty darn straightforward. Problem 3. Same relationships effectively. We have a 4-pole 60 hertz induction motor. So I want you to determine NS. So that's the same equation for NS that we used in part 1 and part 2, but we're using it directly. So we have the number of poles, we have the frequency. So that part's easy. We need to determine the rotor speed at full load. So we use this equation. Since we know slip and we know NS, we should be able to solve for NM. For part C, the slip frequency at full load, that's literally just this equation again. And then part D is the shaft torque at full load. So torque would be so let me think about this here. It should be power over omega M, and our power is going to be the 25 horsepower times 746 watts per horsepower. Yeah. So homework set number 6, real straightforward. Homework set number 7. All right, so now we're given parameters and all of that kind of good stuff, and we're asked to effectively actually calculate things that'll be arguably a little bit more difficult. So in the first problem, we have a 3-phase, 4-pole, 100 horsepower induction motor is rated for 480 volts in delta, 277 in Y at 60 hertz. The motor has the following constants per phase referred to the stator, and then we're given a bunch of parameters, right? RS, RR prime, XS, XR prime, and XM. Total rotational losses are 2950 watts and are assumed to be constant. The core loss has been lumped in with the rotational losses. Our slip is 3 1/3% at rated voltage and frequency. And we are asked to determine rotor speed, power factor, shaft output power, output torque, and motor efficiency. All right, so let's run through this one. really quickly, and let's write down what all of our constant terms are. So P is equal to 4. Fs is 60 Hertz. Our line voltage, which would be our delta connected voltage, is 480 volts RMS. Our rated power is 100 horsepower. And then we have these constants. So RS is 0.1 ohms. RR prime is 0.079 ohms. XS is 0.205 ohms. XR prime zero 0.186 ohms. What the hell happened there? Let's sneak XM in up here. 7.15. Thank you. What other information do we have? All right. So P root is 2950 and our slip is 0.10%. Anything else? All right, so let's write down what we're trying to solve here. So the rotor speed Nm, the power factor PF, the shaft power, shaft torque, and our efficiency. All righty, so let's start with Nm because that seems like relatively low-hanging fruit. So we know that slip is equal to Ns minus Nm divided by Ns. So we can rearrange this a little bit and we would see that S times Ns is equal to Ns minus Nm. And so from here, I believe Nm is just 1 minus S times Ns. So we have slip, we don't have Ns yet, but we can figure that out pretty easily. So Ns is 120 pi Fs over the number of poles. So that, excuse me, not pi, thank you. 120 times 60 over 4. So 120 times 15, I believe, is 1800 RPM. Let me double check. 120 times 60 over 4. Yep, 1800 RPM. From that, we have 1 minus 0.0, whole bunch of threes. 1800 is 1740 RPM. One thing done. All right. So power factor. Trying to think of the different relationships that I know for power factor off the top of my head and how we might utilize those guys. So our rated horsepower is, our rated power is 100 horsepower. So that's effectively the total number of I think that would be analogous to our apparent power here. How would we get average power? Let me look at one of my solved examples. Oh. Okay. So we're going to find the equivalent circuit for the motor, right? So the Thevenin resistance is the stator resistance times XM over XS plus XM squared. So that looks like 0.1 times 7.15 divided by XS, which is 0.205 plus 7.15 ohms square this guy. So 0.1 times 7.15 divided by 0.205 plus 7.15 squared comes out to be 0.094 ohms. And then XThev is just XS, which is 0.205 ohms. So in our equivalent circuit model, we now have RThev, JXThev, and then we're going to have JXR prime, and then RR prime, like so, right? Using our equivalent circuit where we found the Thevenin resistance and the Thevenin reactance so that we don't have that weird middle path anymore. So the equivalent impedance of our induction motor is just going to be R thev plus RR prime plus J X thev plus XR prime. So that is going to be 0.0945 ohms plus RR prime was given to be 0.079. X thev was 0.205. XR prime was 0.186. So let me add this stuff together. So, let's see. Yeah. Okay, so we saw for NM earlier and all of that kind of good stuff. So hopefully that was written down by you guys, but if not, it should be on the video. So let's go back into the power factor calculation stuff. So while my computer was dead, I was explaining to the class effectively that if we have the equivalent circuit for our motor, so this is R thev, JX thev, here's JXR prime, and here is RR prime, like so. We have some terminal voltage V1 applied here, and we should have some current I1 flowing through this equivalent circuit. Our power factor is just going to be the cosine of theta V1 minus theta I1, which is the exact same thing as the cosine of theta ZEQ. So if we can figure out what our equivalent impedance is in polar form, and we take the cosine of the angle of our impedance, that'll give us our power factor, right? So our equivalent resistance in this particular circuit is just R thev plus RR prime. Nope, just doing the resistance, then the reactance, and then we're going to put those together. So R thev plus RR prime is going to look like RS times XM over XS plus XM squared plus RR prime. Putting numbers into this thing, I believe we have 0.1 ohms times 7.15 ohms divided by 0 point something I can't remember, 205 plus 7.15 ohms, quantity squared, plus RR prime was 0.079 ohms. And so putting all of this in my calculator and hoping the computer doesn't just die on me randomly again, I wound up getting 0.1735 and some change ohms. The equivalent reactance of my induction motor is just going to be X thev plus XR prime, where X thev is just XS. So this is going to be 0.205 ohms plus XR prime was 0.186 ohms. Adding those two together. 0.205 plus 0.186, 0.391 ohms. So from this, our equivalent impedance is just REQ plus JXEQ. That's definitely a G. I got 0.428 with an angle of 66.071 degrees ohms. And from here, our power factor is just the cosine of that 66.071 degrees. So cosine of the argument of my previous answer comes out to be 40.56% lagging. Now I need to open that file back up so that I can check that answer, but also figure out what we were going to look at next. Very different. So wildly different. All right. Not having the best day here, apparently, doing math. Zero 0.1 times 7.15 over, hold on, let me get this file open. That's the only thing that would make sense for making a mistake on account of how easy it is to calculate XEQ. So I don't doubt that. That's what I was about to recalculate. Oh my God, it's opening every damn file in the world. I'm getting frustrated. Close this out. Close that out. Don't save anything. All right. So I'm just looking at these numbers really quick. So 0.1, 7.15 over 0.205 plus 7.15. Square that term. 0.0945 plus 0.079, 0.173. Let's look. Nope, that seems okay. Store that as X. Go back over here. 0.205 plus 0.186. Store that as Y. X plus Y gives me that number. Put it into polar form. 0.427 angle 66.071 cosine angle I'm still getting like 40.56 and I literally don't understand why. Double check my equations for equivalent circuits. Okay. Figured out what the issue is. This should be RR over S. Not just RR prime. So that's going to fix some things. So that 0.079 is going to be divided by our slip, which was 0.0333 and all of that kind of good stuff. So effectively what I just found was the impedance of the motor when the rotor isn't moving, which is why the power factor angle was so crazy terrible. So let's try this again. All right, so 0.1 times 7.15 over 0.205 plus 7.15 quantity squared plus 0.079 divided by our slip 0.0 whole bunch of threes comes out to be 2.465 ohms. So that's going to change these numbers significantly, which is going to change that, which is going to change that. Okay. So X plus um, so I wound up getting 2.495, 2.496 after rounding with an angle of 9.014. Son of a bitch, how is that wrong?
Is that a 3?
Yes.
It looks like a 2.
Oh, at this point, I wouldn't be surprised if I couldn't even do that simple math correctly. So, all right. So let me store that in my calculator as A. So the cosine of the angle of what I have stored in my calculator as A, 9.014 degrees, came out to be 98.765 degrees. No, percent lagging. Let's see. Still wildly off. Son of a bitch.
Why is it?
It can be just a decimal, doesn't matter.
And it's 0.988, not 0.8.
Possibly, but realistically, a motor running at 99% power factor seems really high. So let's just throw it all away and look at my solution from last year instead of me trying to do this in front of you, because apparently math is just not in my future for today. Here is giving me craziness. So I think this would have been homework 5 from last year. Let's see what I did with MathCAD. So I found the equivalent impedance. Oh, okay. So instead of using the approximation, I literally just put in the Thevenin impedance directly. I still don't think it should have made a 10% difference like that. So like, why did so like my calculated resistance from the method that we were just using was 2.4 ohms and some change. And here, without using the approximation, we got 2.139. So that's a pretty appreciable difference. That's off by a factor of about 20%. But what's really surprising me here looking at this is that my imaginary part has gone from 0.4 effectively to 1.045. So the approximation was wildly skewing things here. So the approximation that I detailed in my notes, let's just write this down here and look at something really quick. Okay. So I said that if the stator resistance squared is much greater than XS plus XM squared, and XS is much less than X1, then we can use that approximation. Okay. So I would be willing to bet that RS squared isn't much greater than XS plus XM squared, because if we look over here at RS, it's 0.1 ohms. So 0.1 ohms squared is going to be 0.001. XM plus XS is 7.4 ohms. Squaring that, our approximation is effectively invalid here. And so that's the trouble that I just ran into, right? So this condition right here was met. This condition right here was not met. And so I should not have used the approximation that I was using, which is why my answers came out all wackadoo there. Okay. So for the sake of your ease and comfort on the exams, I'm going to make absolutely sure that both of these conditions will be met so that you don't have to worry about the complex math part and you can just use the approximations. Okay, so I'm not going insane. I just made a bad assumption. That's okay. All right, so for the next part of the problem, we were asked to find the shaft power, okay? So let's talk our way through what that's going to look like. So I'm just going through my notes here. Shaft power. Yep. All right, so power for shaft is going to be the input power, which at present we don't know, minus my total copper losses minus my rotational losses. The rotational losses were given to us, right? So yep. All right, so let's talk about how we would calculate these, okay? So I have my voltage V1 here. And then I have the resistance of my stator winding. The reactance of my stator winding. Oh, nope. I'm going to use Thevenin. JXR prime. And then RR prime over S. Here's my current I1. So my current I1 would just be equal to the voltage V1 divided by the equivalent impedance of my motor, using whatever model that I'm using to model my motor, right? My copper losses in my stator, so PSCU, is going to be 3 times the magnitude of I1 squared times the resistance of my stator winding. Okay. So this is copper losses in the stator. My input power should be the magnitude of V1, or excuse me, VS. No, I've been calling it 1 here, but it should have been stator. IS times the cosine of theta VS minus theta IS, which would work. But we could also say that this is the magnitude of VS times the magnitude of IS times our power factor. That would also give us our input power. All right, so now we need to figure out what our copper losses are in our rotor, right? So we learned the other day that the copper losses in our rotor was simply equal to slip times the total power that was delivered to our rotor, right? Well, now we have to figure out what the total power that was delivered to our rotor was. So total power delivered to our rotor is 3 times the Thevenin voltage, sorry, I forgot the V there. Squared times RR prime over slip divided by R Thev plus RR prime over slip squared plus X Thev plus XR prime squared. So if we solve for the power delivered or total power delivered to our rotor, we can plug that in here, giving us our rotor copper losses. And then we can add our rotor copper losses and our stator copper losses together, add the rotational losses to that, subtract those from our input power, and we have our shaft power, which is what we were looking for. Okay. Next part of the problem, we were asked to find the output power. So the power, oh wait, no, that's literally what we just found. Our output torque, okay? So our output torque should just be our output power, can't spell shaft to save my life right now, divided by the angular velocity of the shaft. So that one should be pretty straightforward because we know NM from earlier, which means we know omega M. We just found P shaft, so we have everything we need there. And then lastly, we need the efficiency of the motor. So the efficiency of the motor, memory serves me correctly, is just the output power of the shaft divided by the input electrical power. All right, so after the kerfuffle with calculating the Thevenin parameters, everything else is fairly straightforward. So let's look at problem 2. Different motor, similar situation. Given all of these different quantities, we want the starting torque, we want the slip at which maximum torque is developed, we want the maximum mechanical torque, and then we want the efficiency at maximum torque if the rotational losses are given to be 5,200 watts. So looking back at my notes, specifically dealing with the Thevenin equivalent circuit, we had equations explicitly for our starting torque, which is what we're asking for here, right? So problem 2, our starting torque was given by 3 times V Thev squared divided by the rotor resistance prime over omega S times R Thev plus RR prime squared plus X Thev plus XR prime squared, close that bracket. Right? So it's literally, literally just the direct application of this equation. Using the parameters in the problem statement to find the Thevenin equivalent circuit of the network. Okay. So that's our starting torque. The next thing we were asked to find was the slip at which maximum mechanical torque is developed, right? So that's another just direct application of an equation. So going back to my notes here. Our slip for maximum torque is given by the rotor resistance prime over the square root of R thev squared plus X thev plus XR prime squared. Part B. For part C, we want the maximum mechanical torque. So the maximum mechanical torque, oops, wrong thing. Is given by 3 times Thevenin voltage squared over twice omega S R thev plus the square root of R thev squared plus X thev plus XR prime squared. Like so. And then the next part is finding the efficiency at this maximum developed mechanical torque. So this is the only thing that isn't the direct application of one of the equations that you were given. So let's talk our way through this. Anybody have any thoughts on how we might do this? So we're trying to find efficiency, which is usually defined to be power, the output over the power of the input, right? And we also have something given here that I think our rotational losses were 5,200 watts. No. Well, this one right here is, and this one right here isn't, because if we squared both of them, the units of this would be ohms squared and the units of this thing would be ohms, so they can't add together correctly. I'm sorry, what? So I'll have to double check my solution because it's been a year since I looked at this, but here are my thoughts here, right? So we found the maximum mechanical torque in a previous step. This, by definition, will be the maximum mechanical power divided by the angular frequency at which our rotor is turning. So we could rearrange this relationship to find P max mechanical
would be P max mechanical times omega F. The power delivered to our shaft is just our mechanical power minus our rotational losses. So that's what's going to allow us to calculate P shaft. Our input power can be calculated knowing the equivalent circuit parameters and all of that kind of stuff like we did in the previous problem. So that is how I would approach that one. Let's see what the hell I did last year. It's trying to make me rename my class. So that's just me calculating the input power just using, so this is the input power at the maximum slip. Calculating copper losses because they needed to come out. That air gap power is the rotational power. And so then I said, yeah, my shaft power is my input power minus my rotational power minus my copper losses. Okay, so it looks like I did it a little bit differently, but it should come out to be effectively the same thing. And in fact, I think the way that I just described it would actually be less calculations. But it's literally just using the power relationships that we developed in class. Sean asked if you would be able to have an equation sheet similar to the first exam. At this point, based on how many errors that I have made today, you can bring your whole damn notebook. Just, I wish I had brought mine. That's all I'm saying. So, fully open notes. That's what I'm going to go with. Yep, because if it's bothering me, it's going to bother you. So yeah. Yes, because I don't want you to be able to email each other and all of that kind of stuff. So sorry that you need to kill a tree, but yeah, it needs to be. I'm not going to make you handwrite everything. I'm not going to make you turn it all in because it's fully open notes, but I can't let you use a computer because there's no way to stop you from. Yeah. Yep. So that's what I'm going to go with. For what it's worth, sorry that today was just utterly awful. Just not my day for doing math, apparently.